Today we are delving into the topics where linear algebra actually stops becoming a little bit boring and starts becoming kind of cool. This is the deep facts about linear algebra, and we're gonna start it off with Riesz's representation theorem. I'm assuming that everyone has a little bit of prior knowledge of linear algebra, and of linear functionals and dual spaces and all that. But basically, the theorem says if V is finite dimensional, and then this phi is a linear functional on V, then there exists a unique vector v from our vector space v such that the linear functional expressed on u is the same as the inner product of u with this special vector v. So this special vector v is a unique vector, and then for every u from our vector space v, if we applied the linear functional to u, it's the same thing as taking the scalar product of u with our special vector v. First of all, what is a linear functional? Well, a linear functional is just anything that just takes a vector from a vector space and turns it into a scalar. So a linear functional on on the vector u can literally be defined as, let's say, 2x. Like if our vector v is if our vector v is, let's say, 3, 5, 6, so these are coordinates x, y, z, then our linear functional can just be 2x plus 3y minus z. This can be a linear functional, and that obviously, so x will be 3 in this case, y will be 5, z will be 6, and this will output a number. This will output a number. So it takes vectors into scalars. So a linear functional just takes a vector from a vector space v into our scalar field f. That is what a linear functional is. And the inner product, this is just this is a bit of fancy, because now we're used to the scalar product. Well, we're used to having two vectors. If you have a vector, let's say, like a1, a2, a3, and then we have this is v, and then let's say we have another vector, this is v1, and we have another vector v2, and we can call that b1, b2, b3. Well, then if we take the scalar product with v1 and v2, that's obviously just going to be a1 b1 plus a2 b2 plus a3 b3. You just take the product of each coefficient and add them together, and that again is going to output a scalar. But this is the standard scalar product. You can also define the scalar product completely differently. So this is the standard notation for this is the notation for the inner product between u and v, and the inner product can be anything. We can define the inner product as the integral from -1 to 1 of of u of x times v of x dx. This would obviously be an inner product defined on the scalar on the vector space of functions. So u and v would have to be functions. But again, we could also define the scalar product as the sum and then divide this by 5. So this can be a different scalar product. We don't know how a scalar product is defined, but however we define the scalar product and a linear functional, there always exists a special vector v such that a linear functional can be represented by our special inner product. And that is kind of cool. I mean, that's cool that there always exists such a vector v such that uv will just be the same as this linear functional on u. But then again, it's not even that complicated. It takes a while to get used to, but it's just kind of saying the same thing in two different languages. And we're going to see the proof, and the proof is pretty simple. And then this is going to be really cool. We're also going to talk about how this links to adjoint matrices, and it's gonna be really cool. I mean, this is when linear algebra actually starts becoming even more abstract, but also like cool and interesting. And this has uses in like physics and stuff like that. I'm not gonna go too deep into that, but basically, if we start with the proof, let's say we have an orthonormal basis. So we choose an orthonormal basis. First of all, what is an orthonormal basis? Well, that's just a basis of a vector space, but every basis vector is perpendicular to each other and they all have length 1. So if we have a vector space in R2, well then an orthonormal basis would be this vector and this vector. So 1, 0 and vector 0, 1, they all have length 1 and they're perpendicular to each other. Then R cubed, we'd have 0, 0, 1, 0, 1, 0, 1, 0, 0. So that's what this is what an orthonormal basis is. And now let's just say we have a vector v from a vector space, and of course we can express v in terms of its basis. So we have a1, e1, like this orthonormal basis, I'm just calling it has basis vectors e1, e2 up to en. So a vector v can be expressed as a1, e1 plus a2, e2 plus all the way to an, en, and this is these are just scalar coefficients, and and these are basis vectors. So we can express any vector v as as a sum of the basis. And now the first interesting thing we're gonna notice, I mean, hopefully you should already know this, but I mean, it's a pretty cool thing. We're gonna see what happens if you take the classic inner product with a vector v. I mean, with a vector v and any any of the orthonormal basis vectors ek. Well, this is the same thing as the, v can be expressed like this. So we can just say that this is the inner product of a1 e1 plus a2 e2 plus all the way to an en. So we take this, this is just our vector v, and we take this, we take the scalar product with the vector ek. Now obviously, this just means that we take the scalar product with each term individually. That is what this means. So when we go one by one, this thing will be the same as taking the scalar product with a1 e1. So this first term times ek, I mean not times ek, but we'll have this scalar product plus the scalar product with a2 e2 with ek, plus all the way to the inner or scalar product. I'm just interchanging the two terms with an en, and I mean with the vector an en times ek. So this is we just apply e to all this. So this scalar product or inner product is the same thing as these inner products. And now what we're gonna notice is we can just take the scalar out. So a1 a2, we can just take all of these out. And because these are orthonormal basis vectors, the scalar product with, or the inner product with two orthonormal basis vectors, which are identical, always gives 0. Because again, these vectors are perpendicular to each other. And if we take the scalar product or the inner product with two perpendicular vectors, we will always get 0. That is just a rule. So e1 ek will be 0. So this will be a1. We take a1 out. We're gonna take a1 out. We're just gonna have e1 ek. This will be 0, so this whole term is going to be 0. And again, they will all be 0. The only time when the inner product with two orthonormal basis vectors does not equal 0 is when they're equal. When they're equal, when we have the inner product with ek, then it's going to result in 1. That is a property of the orthonormal basis. So only all of these terms are going to be 0. The only term that won't be 0 is when we're going to have ak, ek, times ek. So all the other pluses are going to be 0. Here we take ak out, so we're going to have ak, ek, and obviously this will be 1. This will equal 1. So this whole thing is just going to equal ak. So what we noticed is if we take the inner product with our vector v and one of the orthonormal basis vectors, ek, what we're going to get is just ak. So it's going to be the scalar coefficient in front of the kth orthonormal basis vectors. That is a very, very cool property, and we're going to use that in our proof, because now once we found that out, if we want to take the linear functional on our vector u, because again, what are we trying to prove? We're trying to prove that every linear functional has there's a special vector such that the linear function can be represented as an inner product between u and v. So taking the linear functional on u, well, that's just the same thing as taking the linear functional on u expanded with its basis. So a1 e1 plus a2 e2 plus all the way to an en. So this is just the linear functional on this guy over here. Before we called it v, but now we're calling it u. And now since the linear functional is obviously and then again, now what we're gonna replace, I was almost getting ahead of myself. What we're gonna do now is, since we found out that ak is just the same thing, these coefficients a1, a2, an, these coefficients are just the same thing as taking v, as taking the inner product, our defined inner product v with the orthonormal basis ek. We can replace all these coefficients. We can replace a1 for v e1. We can replace a2 for v e2. That is really clean, so this is going to be very useful for us, so we're going to do that. So this linear functional is the same thing as the linear functional of v. So these are the main parentheses, and now this is just the notation of how we define the inner product. So v e1 times e1, again this over here is just a1 times e1, so this is this first term here, plus v e2 e2 plus all the way to v en. So this, taking the linear functional on u is just the same thing as this over here, because again, this just equals u. Now, since the linear functional is linear, we're gonna apply the linear functional to every single term in here. We're gonna apply it to every single term in this expression. And notice that these, the scalar product or the inner product always returns a constant value. It always returns a scalar, and the linear functionals don't act on scalars. Again, this will be a scalar. This will be just a scalar quantity. The linear functional doesn't act on that, so it will just leave it alone. So it's gonna only act on the vectors, and the vectors are e1, e2, en. These are, I'm gonna highlight them. these are the vectors, and the other things are the scalars. So this linear function on u will just be the same thing as it's gonna leave v e1 alone, and it's only gonna act on phi e1, and then again plus it's gonna leave v e2, and it's only gonna act on e2, and then plus all the way to it's gonna leave v en, and it's only gonna act on en. So this is what we have so far, and now what we're gonna notice is that this thing, this expression over here is just the same thing as saying so we're also here I was writing v. Someone should have stopped me. Here I was writing v, but we're taking it on u. So obviously, like here I mean u. This like v and u are so annoying, and in math they always use v and u just to confuse you, because they're the two most similar like letters, and they're always used in proofs, which is so annoying. But basically, yeah, this is on u. So now what we're gonna notice is that this thing is the same as saying the scalar product with u and phi e1. I'm just calling it phi e1 times e1 plus phi e2 times e2. I'm going to explain this in a second. Plus phi e3 where this over here is the conjugate, So if this is, if we're doing this over the field C, so if we're doing this over the real numbers, the conjugate of 5 is just 5, But if these are complex numbers like 5 plus I, then the conjugate would be 5 minus I, Just the complex conjugate. This thing, it's the same thing as this thing. Now, why is it the same thing? Well, notice that, I'm just saying this right now, and notice that our special vector v will be this thing exactly here. This will be a vector, this will be our special vector v. But I'm getting ahead of myself. Notice why is this actually the same thing? Well, if we actually evaluate, well, I'm stating that equals this. If we actually evaluate this, well, this is the same thing. We have u, and then we have this special vector v. And if we take the scalar product with this, we're taking the scalar product with each term individually. So again, this will just be the scalar product between u and phi e1, and then we're going to have plus the scalar product of u and phi e2, and and so on. And this will be the conjugate. And inner products over R, they're linear in the first term and on the second term, but over C, if we're over the complex numbers, over the complex field, then inner products are semi-linear on the second term, which means that if we want to take this scalar outside, if we want to take these scalars outside of the inner product, we're gonna have to take their conjugate. So if we want to take this outside, we're gonna have to take. So we want to take this outside, we're going to have to take its conjugate. And the conjugate of the conjugate, is just cancels each other out. So this will just be the same thing as u e1 plus, again, we want to take this outside. So we're going to have to take its conjugate. If this term was here, if this was here and we wanted to take it outside, we wouldn't have to take the conjugate. But if we want to take, if it's at the second area and we're over C, then, it's semi-linear over the second term, so we have to take its conjugate. This, again, there's like a proof for this, for why this is the case. Again, I'm not gonna go too deep into that, but so we'll have this plus all that. So that's just the same thing as this. And then again, now we can see that when I took it out, I get exactly what I started with. I get exactly what I started with over here. So we started with this expression over here. And I mean, here I wrote this on this side, but I can also write this on this side over here. Switching it between here that doesn't require taking the complex conjugate. Here it's written here, it's written here, but we have the exact same expressions. This is why this over here equals exactly this over here. We see that if you evaluate it, we get back to the exact same thing. So we found that our linear representation u can be expressed as the inner product of u and this over here. So this over here is our special vector v. Our special vector v, we can always find it, and it's gonna be v from our vector space v, and it's always gonna be just our linear functional, which we're interested in, evaluated on the first orthonormal basis vector, taking the conjugate times, so that this will be a scalar, and then this will be the actual vector, plus, this seems very weird, but it works. This is how it is. Plus, the complex conjugate of our linear functional evaluated on the second basis vector, times the actual second basis vector, plus, all the way to n. So en times en. This is our special vector v, and we just finished the proof. But the only thing we still have to show is that v is unique. So now what we're gonna say is that suppose, so we show that there exists such a v, but we have to show that there exists a unique v. So suppose that the linear functional on u equals equals u times v1, which is the special vector, and it also equals u times v2. So this is another special vector, v2. Well, if this is the case, well then obviously u v1 minus u v2 has to be 0, because they equal each other. And if that has to be true, then this is just the same thing as saying u times the inner product between v1 minus v2. Again, because the inner product is linear, on the term, so you can just and here you take -1 out, but it's a complex conjugate, so the complex conjugate of -1 is just still -1. So this is just the same thing. The inner product between this vector and this vector is just again, is just equal to this. So you just apply the inner product to each vector individually. And this is true for every u in v. For every u in v. And notice that v1 minus v2, well, both of these vectors are in v, so their difference is also in v, because again, vector spaces are closed under vector addition. Now, since this is true for any vector in v, we can say that u equals v1 minus v2. It also has to be true for this vector, because this is also from v, as I just said, which means that we have to have the v1 minus v2, which is our u now, the inner product with itself has to be 0. But whenever we have the inner product between two vectors, v and v, whenever we have the inner product between two vectors and it equals 0, the only way that's true is if v itself equals 0, which means that v1 minus v2 have to equal 0, which means that v1 has to equal v2. So we just showed that if there exists, this special vector v such that, from the Riesz representation theorem, it has to be unique. So we just finished the proof. And we see that this is why v does not depend on the chosen orthonormal basis. We choose an orthonormal basis, and then we compute this special vector v, e1, e2 to e, and this is an orthonormal basis, but it doesn't depend what kind of orthonormal basis we choose. As long as it's orthonormal, we see that, it will always be the same. But it does depend on your chosen, linear functional. If we chose a different linear functional, we'd have different, we'd have a different special v, and if we also chose a different scalar, if we defined a different inner product, then not the standard one, then again our orthonormal basis vectors would also change, because if you define a new orthonormal, if you define a new inner product, you also define the new perpendicularity. I don't think that's the word, but if two vectors are perpendicular, this is what it means that two vectors are perpendicular in the normal inner product. But in a special inner product, we could say that these two vectors are perpendicular. They don't have to be 90 degrees away from each other. That's only the case for the normal, for the standard inner product. And that's basically it. That is the end of the proof. Now, if anyone still wants to be watching, I'm going to do a short example, just so it actually makes a bit more sense. So let's say we have the classic scalar product, the classic inner product. And so, when we just have, and I'm talking over a vector space R2 now. So on R2. So if we just have a vector x1, x2, and then a different vector y1, y2, then we can say that the scalar product between these two will just be x1, y1 plus x2, y2. That is this times this plus this times this, and that is the classic the classic inner product. And we can say that our linear functional f on our vector x1, x2, so just any vector, will just equal to x1 minus x2. So this is our linear functional. This is our linear functional, which again takes a vector, like 3, 4, then outputs a scalar. It's going to be 2 times 3 minus 4. So that's going to be what, 6, 2. So yeah, that is our linear functional. Now we're saying that there exists a special vector such that this linear functional f can be represented as the scalar product between our vector, how are we going to call it? Our vector u and the special vector v. So basically, 2x1 minus x2, this linear functional, on v, this linear functional f, on u, this linear functional f on u, it's just the same thing as 2x1 minus x2 is just the same thing as the inner product between our vector u, and our vector u is just x1, x2, and our special product, our special vector, which I can just call ab. So it's gonna have coefficients a, b. And now, now what we're left with is just normal algebra. We have 2x1 minus x2 equals, here we take this classic scalar product, so we have x1a plus x2b. that is what we're gonna have, and then with some little algebra, we're gonna see that b has to equal -1, a has to equal 2. So our vector v such that this holds will be 2 minus 1. And that, and then we could define the scalar product completely differently. If we're looking over the vector space of functions, we can define our scalar product as the integral from 0 to 1 of f of x times g of x dx. And then again, we can use the same thing again, and let's say we have a linear functional on f, and that's going to be the integral from 0 to 1 of, let's say, 1 plus 2x f of x dx. Again, if we want to find the special function g such that this holds, if we want to represent the linear function of f with the inner product of f and a special function g, we want to find this unique g. Well, then we just equate this to over here and we solve. And here we see that g has to be exactly this. But again, this is how we solve it. And if you don't feel like equating integrals and solving that, if you're too lazy for that, well then you can also just use the other method where you can say that you can find an orthonormal basis. You can find the orthonormal basis of your vector space. So if you're looking at functions, if you're looking at the polynomial vector space in R3, let's say, your orthonormal basis would be 1x and x squared. This is for R3 on polynomials. But if you don't feel like equating this, then you can just say that your special let's say function v or vector v or whatever will just be your linear functional evaluated on the basis vector e1 times e1 plus boom boom plus all the way to your linear functional en evaluated on en. So you can either do it this way, or you can just find you can find an orthonormal basis which is orthonormal in respect to your chosen inner product, and then you can find your special vector v by just applying the linear functional to each of the orthonormal vectors, taking its conjugate, and then and summing it up. So this is and you can get the orthonormal basis with the Gram-Schmidt process. Whenever you define a scalar an inner product, you can find if you have a basis for your vector space, you can find you can change it to an orthonormal basis through the Gram-Schmidt process. And now, okay, how long is this video? I don't want to make it too long, but I just want to have a cool fact with the adjoint. So again, if anyone is still interested, you might know if you took a linear algebra class that if you have a linear transformation, t from your vector space v to w, or I can just say t from v to w, then you can define the adjoint. Oh my goodness, you can define the adjoint of t as, you can say that the adjoint of t is this special matrix t star, and this would be a transformation from v to from w back to v. And the its characteristic will be that tvw. So v and w are vectors. If v and w are vectors from your vector space v, well then the inner product between your linear functional tv, between this vector and w, is the same thing as v times. Is the same thing as the inner product with v, and the adjoint of t times w. So this is kind of the product. If you define your scalar product, then tvw is the same thing as vtw when you take the scalar product. And this also looks kind of weird at first, but it actually makes a lot of sense if you just think about Riesz's representational theorem. Because what is this over here? Well, we have a vector v from v, and then what we do is we multiply. We apply a linear transformation to v. And then we take the scalar product with the vector w, and w actually, I said this wrong, w has to be from the vector space w, because v is from v, t takes our vector v from v to w, and then w is also has to be in w, so that this whole thing is going to happen in w, in the vector space w. But basically, for any v from v, we take this scalar product. We multiply t by this transformation. Take the inner product with w. So what we're gonna get is a scalar. So this is a function that takes a vector and puts it into a scalar. So this can be our linear functional. So now we know by Riesz's representation theorem that let's say if we fix w, we know that if we have this linear functional on v, then this linear functional has to equal our vector v times a special vector u, and this special vector u just so happens to be the adjoint of t times w. So if we fix w, this linear transformation, which is tvw, has to equal v times a special vector u, you know, which you can find on a Riesz's representation theorem. V will just be this over here, and that just so happens to be the adjoint of t multiplied by w. You know, this has to hold, you know, if w changes, then, you know, your special vector u is going to change. But, you know, for every w, your special vector u will change. But this, you know, you always multiply w. Your special vector u will always be your w times, you know, times the adjoint of t. And that's just a cool fact. And then again, you know, the adjoint, we can go even deeper into the adjoint. The adjoint is just the transpose of t if you're looking at it from an orthonormal basis. But I'll probably talk about that in another video. So that is it. That is all I wanted to cover. I mean, I probably went over it kind of fast. And, you know, sometimes I switched up u and v, but I hope I corrected everything. I hope it makes sense. You know, this is pretty cool. This, you know, deeper linear algebra. But, you know, this is when linear algebra actually starts getting applied to cooler stuff, you know, and it's not just basic, you know, matrices and determinants and, you know, and eigenvectors anymore. But yeah, so I hope you enjoyed. Thank you for watching, and see you next time.